Last time I started to talk about the phasors and impedances. I talked about how if we have a sinusoidal wave, we can write it as a phasor, or in other words, we can write it as a um, complex number, and then how we can convert the resistance or the inductance or capacitance to a complex number called impedance. Now I want not to start to talk about actually now if we have the steady state AC circuit with the sinusoidal, for example, source, current, or voltage in that, how we can actually analyze those kind of circuit. The steps that we want to take away is using these the, mm, actually uh, these two phasor and impedance. So what we will do that is that when we have the AC circuit, the very first step that we will do is that we convert all the sources uh, into the phasor. So any voltage or current that we have, just convert it to the or write them with the mm, replace them with the phasor. So other words, so mm, convert all sources, and basically these are going to be the sinusoidal forces, sinusoidal sources to phasor. That's the very first step that we are going to do. So if you have, for example, if you have the voltage, that's going to be the VT is going to be the V max, and then we have cosine omega t plus theta. I assume I'm going to call it theta 1 just in case that. Then we will write it as a phasor, so we will write it the V is going to be the V max with the angle of theta 1. So we write the voltage as a phasor, the same as if we have the current, and it's going to be the uh, I max cosine omega t plus theta 2. Then we write that as I is equal to I max with angle of right, so write it as I is equal to I max with angle of theta 2. So any sources that we have is the voltage or current sources that's going to be in sinusoidal form. We are going to just uh, uh, write them as uh, phasors. Just remember, if you have a if you have for example you have combination of the AC and DC source, the DC source, for example, if you have the V and it's going to be constant, for example, the V as T is going to be 2, assume. If it is constant, so you can write it as V is the, for example, that 2 is your, and the angle is actually 0. So remember, if we have anything on the real world in the is only a real, sorry, if we have anything that's is not sinusoidal, you just can put it into the phasor mode like that. So it's magnitude, and then with angle of 0, then it's going to be the only thing you need to do is just put the angle of 0 there to convert it to uh, phasor format. If you have it in uh, if you don't, if it's not sinusoidal form. Anyway, so the next thing that, so this is the very first step, convert everything you have in sinusoidal form into the phasor format. And then the next step that you want to do is that go ahead and replace all resistance, inductance, and capacitance with impedances. So all the resistance, inductance, and capacitance you have it, just rewrite them as impedance. So how is it going to work? If we have for the inductance, for the inductor, we know that if we have the inductor of with the inductance of L, so that's why inductance of L, then the impedance of that is going to be the ZL is going to be J omega L, or it's going to be omega L, and because it's a J, so it's going to be on the, it doesn't have any real value, so it's going to be on the imaginary angle, so it's going to be 90. So replace, so if you have any inductance of L, it's going to be the impedance of that's going to be this. If you have the capacitance of C, then the inductance of that is going to be negative J divided by C W, or you can write it as a 1 over C, sorry, omega, not that was C omega. And we, again, because it's the negative J, means it's on, it doesn't have any real part, this only has the imaginary part, and because it's negative, it means going downward, so it's going to be negative, angle of negative 90. And for the resistance of R, the capacitance of R is just R, or you can write it with R with angle of 0 as here. So it's not going to be much difference from that. So it's a constant. So it doesn't have any. The theta is actually 0 because it's going to be on the horizontal axis of the real value. So any L you have in the circuit, so anywhere you have the L, replace it with ZL. Anywhere you have C, replace it with ZC. Anywhere you have R, you actually leave it as it is or replace it with ZR. So then we have the new circuit that the sources in our circuit are written as a phasor like that, and the inductance, capacitance, and resistance are written as impedance like that. When we have these two, when we have the new circuit with the phasor and impedance, the third step is that assume impedance as a behave as a resistance. Just analyze a AC circuit the way we analyzed circuit with resistor. So assume all this impedance, in other words, assume all in this impedance behave like a resistance. So assume you have a circuit that everything in that circuit is resistance with and instead of having get resistance of R, they have the resistance of uh, impedance. So by the time you get to this point, the rest is very easy because you're going to assume everything behave as a resistance, and the same as what we did with the resistance. When we want to, for example, if you want to find the equivalent resistance, if they are in series, just add them together. If they are in parallel, do whatever we did. Any formula or any method that we used it, for example, node voltage method, the mesh current method, all those methods that we use it for the resistance, just use them. Anywhere that whatever you use it, just use this one. The same here also, all the, for example, the Kirchhoff law would be applied. For example, if if we write the KVL, we can write the KVL is as the same. So we can write the voltage in any closed loop is zero, or we can write the KCL as well. So we can write the sigma I in any uh, I would say the any node is going to be zero. So the very same thing. When you get to that point, anything that we have, the Kirchhoff laws, the node voltage method, the mesh current method, the voltage divider method, the current divider method, equivalent method, everything, we use it the way as we use it for resistances. And I'm going to show you some example, and through the example, you will see what I mean. So let's look at an example, how to uh, analyze a AC circuit. So assume I have a sources here, um, the voltage sources, the AC voltage sources that's connected to um, a resistance, and then goes and get connected to inductance, and then it goes back toward the capacitance, and then it goes back to the source. So here I know that is the VT, and I know that the VT is equal to 100 cosine 500 T plus 30. So this is the voltage, so it's the AC voltage. The R here is 100 ohm, and then here the L is 0.3 henries, and C is 40 microfarad. So I want to see how we can analyze this simple AC circuit and find the current and voltage in all the elements that we have. So the very first step, as I said, the first step, we are going to convert all the sources to phasor. So I'm going to come here and says the VT is 100 cosine 500 T plus 30. Then I'm going to convert it to the phasor, so I know the V is going to be 100 with angle of 30. So it's going to be my voltage. So if I come here and start to draw that, so I can come here and say, okay, draw voltage. So I have a source, and the source, the voltage in my source is going to be, so let me make it VS. So and so we know that the voltage at the source is 100 with angle of 30. Now I have to go ahead and rewrite all the resistance, inductance, and capacitance as the impedance. So the very first I need is the omega. How much the omega? Look at here, I have 500 T. So if I look at here, this is the omega T. This is the omega T. Therefore, the omega is 500. So now I can go ahead and write each of these as an impedance. So for the R, I know that the ZR is just R. So it's going to be 100. Oh, so what I'm going to have here, this is going to be the same. So when we are dealing with the resistance, it's going to be the same. So I know that it's going to be the ZR and it's going to be 100. Then I have to find the ZL. For the ZL, I know that the ZL is the J omega L. So it's going to be J. The omega is 500. And then times L, which is 0.3. So it's going to comes out as J 150. So I will move ahead here, and then I have the inductance with the ZL is going to be J 150. And then I have to convert the capacitance also to impedance. So I know the ZC, the impedance of the capacitance, is going to be negative J divided by omega L, which is going to be negative J divided by 500, omega C, not omega L, omega C. So it's going to be times 40 times 10 to the negative 6. So if you do the calculation, it should comes out as negative J50. So then I have the capacitor. And the capacitance converted to impedance as a negative J50. So now I write everything in format of the you're looking here as in format of impedance. By the time and phasor. By the time I get to this point, I'm gonna just simply assume everything is behave as a resistance. So assume this is a resistance with the is the impedance, but you can assume it is the resistance with the resistance of 100. This is a resistance with the resistance of J 150, and this is a resistance with resistance of negative J50. You can assume it like that, and then solve it. The same as you have 3 resistance here, so it was similar that you have a DC source and 3 resistance in series. So if I want to solve that, assume what I'm going to have here is I'm going to have the current goes through this, that this current is going to be I, and I have here is this one is VR, this one is the VL, and this one is the VC. So to find the I, the easiest way that to find the I is that go ahead and assume, as I said, assume there are three resistance in series. So if you have three resistance in series, just find the equivalent resistance. So I can go ahead and say the equivalent resistance here can be something like this. So I can say I have the drug, the let me put it there. So it's going to the VS, that's VS here, and then I have an equivalent impedance here. So assume I add these three, because so it's going to be Z equal. So I'm going to write the rest here. So if I go ahead and find the Z equal, as I said, assume they are behave as a resistance. So we have three elements in series. So if they are in series in the resistance, we just add all the resistance. Now we add all the impedance. So it's going to be ZR plus, it's going to be ZR plus ZL plus ZC, and this is ZC here. ZC. So it's going to be 100 plus J 150 and minus J 50, which is going to be 100 plus 100 plus J 100. So add all the real part together, add all the imaginary part together, and you can write that in the polar. So it's in rectangle in a polar format is 141.5 with angle of 45. So remember that again, to convert from this one to that one, you can use any of the equation that we use in the complex when I was explaining the complex number, going from the rectangular to polar or vice versa. Or you just, if you have a almost all the engineering calculator does that. So you can enter this and get that, or you can enter this and get that. So make sure you know how to do that, so you're not gonna um, spend any time to convert these together. Simply can enter it into your, or even this, you can enter this in your calculator, get this or this one from your calculator. Now look at here. So the I have here is going to be the same as the I here. So I can go ahead and calculate the I, the same as we did it before. Remember that we said that if you have the DC, in the DC we have the V was the RI, the equation. If you have the impedance, we just change it as instead of R, we change it to Z. So instead of having this, we write it the V is equal to Z I, in similar to the Ohm law. So here the V is 100 with angle of 30, and so this is the V. Well, let me write it here. So I can write it. So the VS is Z equivalent I. So I can go ahead and say it's going to be 100 with angle of 30 is equal to this one, 141 with 141.5 with angle of 45 times I. So I can go ahead and say the I is 100 with angle of 30 divided with 141.5 with angle of 45. So again, the easiest way is that just plug these two in your calculator and your calculator give you your final value. But if you want to do it manually, remember when we have two complex numbers divided, so we divide the magnitude, so it's going to be 100 divided by 141.5, and the angle is the difference between them, so it's going to be 30 minus 45. So eventually you're going to get 0.707, I think, with angle of negative 15. Or I said you can plug this into your calculator and directly get this value. So as you see here, to find the I, everything is just the same as we did it in the resistance. Add all the impedance together, similar as we did for the resistance. Then use this equation, which is similar to the Ohm law. So it's a voltage. So this is the impedance and the current. Add all the numbers in there. The rest is just complex number calculation. As I said, if you have the um, uh, if you know how to use your calculator, it's very easy to use. Now I can convert this back to from to sinusoidal form. So if this is the I, so I can say that the the I in t. So here, if I go ahead and say, if I have here is the I t, so I can come here and say the I t. So I can convert it from the phasor to time domain. So it's going to be, this is the amplitude cosine omega, which is 500 t, plus theta, which is going to be negative 50. So this is the IT that we have it here in case that we want to know how much is the I in the time domain. The next thing is that I have to go ahead and find the voltage in each of these um, elements. So if you look at here, it's not that much difficult anyways, because we have this V is equal Zi. So I can write because I know the I know the Z for each of them. So I can write the V equals Zi for each of these uh, three, and then get the uh, value for each of them. So I will start from the resistance. So let me go there. So for resistance, V in the resistance is ZR, which is basically R. The ZR is the R. I just write it like that. So it's going to be um, similar to the other one. So the VR, the R was 100 ohm, and the I was 0.707 with angle of negative 15. So, so basically, if I go ahead and do the calculation, it's going to be 70.7 with angle of negative 15 volt. It's going to be my voltage in the resistance. The same for the capacitance. I'll go ahead, it's going to be the ZL times I, and the VL is going to be the ZL, and the ZL was J 150. So that was the ZL. And then times the I, which is 707 negative 50. Now to do the calculation, I have to convert this to the polar format. Remember, if we are multiplying or dividing, it's much easier to do the calculation in polar format. And again, if you have it, you can just simply put it in your calculator and get it in the polar. But remember, because this one doesn't have the um, real value, you can simply just um, use it as convert it very easily, convert it to polar form. And remember, if I said if the z value is only the jy, then the z value is the magnitude is basically is the y with angle of 90. We had it before. Um, if you have something like that, but again, you can simply enter it in your calculator and get it. So then the and also we talked it before that the impedance for uh, the impedance for the L, also we know that is the impedance is j omega L, or it's going to be omega L with angle of 90. Anyway, any way that you convert it just to um, as I said, to the polar format. So it's gonna, then the VL is gonna be 150 with angle of 90 times 707 with angle of negative 15. So again, we times these two, either plug it in your calculator, or when we times it, we multiply the magnitude and we add the angle together. So it's going to be 150 times 707 with angle of 707 with angle of 90 plus negative 15. So VL eventually would comes out as 106.1 with angle of 75. And the same thing with for the VC again. The VC is ZCI. So the VC is negative J50, and the I is 0.0707 with angle of negative 15. And then you can convert it again. So this was the ZL. We know for the same thing for the ZC was negative J divided by omega C, or it was 1 over omega C with angle of 90, negative 90. But again, the easiest way of that, also we know that if the Z is negative JY, then the Z is Y with the angle of negative 90. So either put it in your calculator, convert it to polar format, use this equation to convert it to polar format, or use this equation to convert it to polar format. Either way, the easiest way is just put in your calculator. So the VC is going to be, if you convert it to the polar format, so it's going to be 50 with angle of negative 90 times 0.707 with angle of negative 15. And then, so because they're multiplying, we multiply the magnitude and we add the angle. So it's going to be 50 times 0.707 with angle of negative 90 plus negative 50. So VC is coming out as 35.4 with angle of negative 105. Again, remember that If you know how to plug it in your calculator, you just can plug this and this in your calculator and you get this value. So you don't need to do any of these middle steps. Just learn how to put this in your calculator. So these are the VR, VL, and VC that we have, and we have the I. So as you go back, I calculate the I, VR, VL, and VC for all these three in polar format. And if we need, we can go ahead and convert any of them to time domain if we need it. The same as we did it here for the current that we converted from the phasor to time domain. If you need it, you can go ahead and convert any of these back to the time domain if you want. One last thing is that I just want to draw each these phasor. So I have this VR, VL, and VC and the I here as a phasor. So I just go ahead and draw them to see how they actually look like if we there are these values in a complex format. So if I go ahead and try to draw them here, and it's called the phasor diagram. Basically, it means that we draw each of these phasor in the polar format. So each of them has the magnitude and angle. So I will go ahead and start to draw. The very first one is going to draw the I. So the I, the magnitude is 707 with with magnitude of negative 15. So that's the very first thing I'm gonna to draw that. And I'm not gonna draw it in the scales, probably I can't. So 707 with angle of negative 15. So it's gonna be the I. So whatever is magnitude. And this angle is gonna be negative 15. Then the next thing I have is the R, and you can see the R has the same angle with the I. So both of them are negative 15, but with different magnitudes. So I'm gonna draw the R with different color. So it goes exactly the same angle with the I with different magnitude. So the same angle. And let's see if I can remove the so this was the I, and this is the R, and the angle is negative 15. So this is the I. Then if I draw the source, the voltage at the source, and let me draw the voltage at the source. So the voltage at the source is the 100 with angle of 30. So the length is 100. Again, I'm not try to keep the length relative. The length probably not going to be correct, but the angle I try. So it's going to be the 100 with angle of. So it's going to be the VS with angle of 30, and this is the VR also, not the R. So it's going to be the VR. And then we have the VL and the VC. The VL is 106 with angle of 75. So I choose another color. So it's got 106 and with angle of 70. So this is the 75. This angle is 75 degrees. And the magnitude of the VL, which is 106. And the very last one is the VC, which is the negative 105. And then if you draw it, it's going to be right here. So it's going to be the magnitude of 35 and the angle of the negative 105. So it's going to be the VC, and this angle, if I can show it, is negative 105. So if you look at here, we will see that the voltage and the resistance and the current has the same phase or same phase angle. Both of them are the same phase angle. If you look at the VC is happened before that the I, so we will say that the VC lags the I with and it's if you so this is 90 degrees, so you see the VC lags the I with 90 degrees, and the VL leads the I, leads the current. So it's the VC and this is the current. So the VL leads the current by 90 degrees. If you look at that, so it's the 75 and 105. So VL leads the current by 90 degrees. VC lags the current because before that with 90 degrees. So it's showing the phasor of all these voltage and current for this problem. So one more time again. So there is the easiest way of doing all these things is that whenever you have the circuit in AC, convert all the source to the phasor, convert all the resistance, impedance, resistance, inductance, capacitance to impedance. And then after that, just assume you are doing everything as you do it with the pure resistances. The only thing is that the calculation is going to be in a complex number. And if you know how to put these complex number into your calculator, you can do it very easily. So let's look at another example of how we can analyze the circuit in complex domain. It's analyzed in AC domain. So again, assume we have sources here, and that source is the Vs is a time dependent source is equal to 10 sine 1000 t. So this is the source. Then it's connected to inductance with 0.1 henries, and then there's a resistance here with 100, so R is 100 ohm. And then there is a capacitance parallel with, so it's going to see with 10 microfarads, and it has the so assume this voltage here is because these two are in parallel. So if it has a VC, it has the voltage of VC here and here, and by the way, because these are parallel, they're going to have the same voltage because they're connected to the same nodes. So assume this is what we have, and we want to analyze this circuit to find the VC as a function of time. So if we have this, again, the very first step that we need to take is that we go ahead and convert all the sources to the phasor. So I have the Vs is 10 sine 1000 t, and you see it is in sine, so I have to convert it to cosine. I cannot use it this way, so I can go ahead and write it as 10 cosine, and remember to convert it to the cosine, we just subtract 90 from that. So it's going to be converted, so therefore I can write the Vs as, in the phasor format, is going to be 10, the magnitude is 10, and the angle is negative 90. So I go ahead here and said, okay, so therefore I have a source with Vs, which is going to be, let's write it. So I have the Vs, which is going to be 10 with angle of negative 90. So probably I have to write it as. So that is my source. So the source converted to phasor. Now I have to go ahead and convert each of these impedance, resistance, and capacitance, the inductance, resistance, and capacitance to impedance. So for this one, the ZL, we know that the ZL is again J omega L. So it's going to be J. And look at here. So this is omega T again. So therefore omega is going to be 1000. So it's going to be J times 1000 times 1000 times 0.1. So we have it as a J 100. So it's a ZL. For the R, it's going to simply is going to be R. So we know the ZR is just R. So it's going to be 100. And for the C, it's going to be negative J divided by C omega, which is going to be negative J divided by or the omega C. Usually we write it, so write it the same way. So it's going to be omega C. So the omega is 1000, and then the C is 10 and times 10 to the negative 6. And if you do the calculation, it comes out as negative J 100. So now, now we have them in this form. So also, if you want for the fair, because usually we are going to need uh, the angular format as well. So we know that again, we know the ZL also is omega L with angle of 90. So you can just simply here convert that to, if you do the calculation, it's going to be 100 with the 90 degrees. Also, we know that the ZC is 1 over omega C with angle of negative 90, which is, if you do the calculation, it's going to come at negative 100 with angle of negative 90. In case that, because usually we are going to need both format of that. We are going to need the rectangular format, and we are going to need the polar format as well. Anyway, so now I'm going to put here, so I have the the inductance with the impedance of ZL, which is ZL is J100 here. Then I have a resistance, which its impedance is the same as its resistance, so ZR is 100, and then I have the C, the capacitance, which is Z is negative J100. By the time I get to this point, the rest is that I can go ahead and start to, I would say, um, assume each of these just behave as a resistance. Just assume this is a resistance with this complex number resistance. This is a resistance with this value, and this is a resistance with this complex number resistance. And then do all the calculation the same way as we did it up to this point. So the next thing that we want to do is that we want to find the voltage in these two elements. So to find the voltage in these two elements, we know that the voltage in this one and this one is the same. So I can go ahead and find the equivalent of these two. Find the equivalent of these two, actually these two. Assume they behave the same as a resistance. So I'm assuming this is a resistance, two resistance in parallel. So whatever voltage I have here, the same voltage I have here because they are in parallel. So I can find the equivalent resistance, or in this case, impedance. And whatever voltage I find for that equivalent element is the same for this one or this one. Because we know that when the elements are in parallel, the voltage in each of them is the same. So I can go ahead and say, let me draw the rest here. So I can, the very first thing is just go ahead and say, okay, I'll find the equivalent of these two. So I'm gonna have these Vs, which is gonna be, so it's gonna be my Vs. And then I have on here is gonna be the ZL. And then I have an element here, which is gonna be the Z equivalent for the R and C. So the Z equivalent for the R and C is that we know they're, as I said, they'll behave as the resistance, considered as the resistance. So assume you have two resistance. One has the resistance value of 100, one has the resistance value of the negative J100. So how you find it? The same as we did before. So it's going to be, they're in parallel. So it's going to be 1 over 100 plus 1 over negative J100. And then just if you plug it in your calculator and do the calculation, eventually what you are gonna get is 70.71 with angle of negative 45. Or you can do the calculation manually, the same as you do before. So this is going to be the equivalent here that we have. Now, if I find the voltage in this one, whatever is the voltage, this one is going to be the same as the voltage in the ZC or ZR, because they are parallel, and this is the equivalent. Whatever is the voltage in the equivalent one is the same as the voltage in each of the original one. So now I can go ahead and try to work on that. So before I actually go ahead, let me rewrite this as before. So in case that you want to do it by hand, you know how to. After you actually do the calculation, eventually you are going to get 50 minus J50. And then if you convert it to polar, it's going to be 70.71 with angle of negative 45. Now I want to find the voltage in this one. But similar to what we did, for example, one way of doing that was like what we did before. Just go ahead and um, try to write the Kirchhoff law or any other way that you think is easier to work with to find that. But probably the easiest way is the voltage divider method. And if you remember, so if I said, and this has the voltage of VC, and here is the voltage of VC, the VC is the Vs, because again, assume these are just uh, resistance. So this is, assume this is a resistance, assume this is a resistance. This voltage is going to be divided between these two resistances. So how it's going to be divided? In direct relationship with their resistance, if both of them were resistant. So it's going to be the Vs times the relation of this. So it's going to be the um, in the ratio of the, so ZEQ for RC divided by ZL plus ZEQ for RC. So it's gonna, so the Vs, how much the Vs is 10 negative 90, and the ZEQ for the RC here is 50 negative J50. And then down here, again, we have the ZL, which is the J100, plus the Z equivalent, which is going to be the 50 negative J50. So again, if you do all the calculation or plug it in your, it's easier, as I said, when we do the division, it's easier to do the division in or multiplication in polar format. So I can go ahead and convert everything to polar format. So it's going to be 10 with angle of negative 90. And here we already know it's going to be 70.71 with angle of negative 45. And here, if you add them together, which gives us the um, 50 plus J50, and then convert it to polar, you're going to get 70.71 with angle of 45. And then if do the calculation here, you divide these two, so basically divide the magnitude and subtract the this angle minus this one, and then multiply it by this, which multiply the magnitude and add the angle. So if you do all the calculation, eventually you're going to get 10 with the angle of negative 180. And this one I just write it in case that you want to know how much it's going to be. 50 plus J50. So again, as you said, you can do this manually, or you can simply plug this in your, if you even plug this in your calculator, it's going to give you this magnitude here. But remember, whenever you want to add or subtract, it's easier to add or subtract the complex number in when they are in the rectangular format. When we want to divide them and multiply them, it's easier to do them when they are in the polar format. And as I said, when we are dividing, divide the magnitude, subtract the angle. If you are multiplying, multiply the magnitude, add the angle together. So if I come here, so this is the VCs, and I can write it if I want it as a time format. I can just simply go ahead and write it in the cosine format. So it's going to be 10 as when you cosine the omega t. The omega t is 1000 t, and plus the theta, which is the theta is negative 180. 18. So I can write it like that. So fix this. So VC is going to be T. As I said, the VC here is the same as the VC here or is here because these two are polar. As soon as I find the VC here, I can say the VC for the other two is the same as well. Now, if I want to find the current assume I want to find the current in each of these three elements here, here, and here. What's going to be? So I know that I have the current here, for example, it goes here. It's going to be I. And then I know that this current is going to be eventually this I is going to be divided here to IR. And then the other part is going to be here to IC. So I want to find these three I. The first I is the I that goes through L, so I may, and then this will go to I and this go to C. So the easiest, the first step again, assume I have three resistance and want to find to this I. To find this I is that I have to go and find the equivalent of these three and then find the I for that. So let me go to the next page. So then I'm going to find the VS. So I have the VS, and then I want to find the equivalent of all three. Let me say here, all these three together, or basically I have this, and I want to convert it to next one. So let me go. So I have this one as ZL, and then I have this one as so this is the ZL. So this is the ZL, and this is the Z equivalent for R and C. Now I want to convert it to only one. So I have the VS, and then I'm going to have only one element here, which is going to be ZEQ. So it's going to be the equivalent for all of them. So I know that ZEQ, again, assume these two behave as the resistance. So I have two resistance parallel to equivalent one is going to be, just add them together. So it's going to be ZL plus ZEQ of the RC. For the ZL, we know the Z for L was J100. And then the ZEQ that we find it was 50 negative 50 J. So J50, which eventually it will comes out as 50 plus J50, or as I said it also for it's going to be 70. This is 70.71 with angle of 45 if you convert it to polar format. Now that we have this, so I can go ahead and note that I here also is the I here. Still is going to be the I here. So now I can go ahead and say that V is the ZI. So therefore, the VS is the Z equivalency times I. So the VS I know is going to be 10 negative 90, and that we have it, and um, is equal, and this is going to be 70.7145 times I. So therefore the I is just divided by 70.71 divided by 45. So again, either plug it in your calculator, get the final value, or if you want to do that, divide the magnitude and subtract the uh, angle. So it's going to, because it's a division, 71, and subtract this one from this one. So it's going to give us 14 angle of negative 135 degrees. So this is the I. And similarly, we can find the for the C. So we can go ahead and say the VC is ZC, that I goes through the C. And because we know the VC, we know the ZC, so we can use them. So the VC that we calculated from the previous step, the VC is 10 negative 180. So the VC is 10 negative 180. And the ZC that we calculated, we can use it in polar format here, because we do the multiplication. It's easier to um, use it in the polar format, which is going to be a negative. Sorry, it's going to be the 100, not negative. Um, what was that? So yes, it's going to be 100 negative 90 that we have. So it's going to put it here, the same here as well. So it's going to be the ZC is going to be 100 negative 90 times IC. And then if you do the calculation, again here, the IC is going to be 10 negative 100 divided by 100 negative 90, which is going to 0.1 with angle of negative 90. And the same for the R. VR is just ZR. I go through the R, and again, the VR and the VC is the same here because they are parallel. The VR and the VC is the same because both are parallel. So so we know that the VR is the same as the VC. So again, it's going to be 10 negative 100, and the ZR is just 100 times IR. And then if you do the calculations, the same here. So the IR would comes as 0.1 with angle of 0.1 with angle of negative 180. So these are the volt, the current in each of these elements that we have. Again, we can go ahead and draw the phasor diagram just to show how the phasor behave. And if I go ahead here, so again, I draw the I first. So the I has this value with angle of negative 135. So I'm not gonna keep the scale correctly. So try to draw the angle correctly. So it's gonna be, this is the angle, so negative 135, and then we have the so this is the I, and then we have the IC, which goes here. So this is the IC with the negative 90 that we have it. Then we have IR that has the negative 180. So the IC that goes negative. Sorry, so this is the IC. So it's the IC with negative 90, and this is the IR with negative 180. So this is IR. So it's the IR negative 180 is the IC with the negative 90, and the VS as also as we have the VS. If you go back here, is the negative 10 with the negative 90. So if go ahead, draw the VS as well. So the VS is also going downward because it's a negative 90 as well. So it's going to be somewhere here, and it's going to be the VS. So you can see how these three um, um, in the phasor format, how they located respect to each other.